Okay, good afternoon, everyone. Welcome to this my YouTube channel. This is Mass Mastering Academy, and I really appreciate the fact that you are here today studying with us. Please, if you are new here, kindly subscribe to this channel, and if you have not done so, help us and do so that the channel can grow and reach to other people in need of some mathematics topics. Also, help us to share this to your friends, your colleagues, and in your group. Thank you very much. Really appreciate. Today we are looking at reanalysis 1, and in the reanalysis 1 we are looking at how to prove that every differentiable function is a continuous function. He said we should prove that every differentiable function is a continuous function. How can we prove this? Take note of this. Okay, let's look at the solution. Okay, say let f be differentiable at x naught. That x naught, this x naught is a specific point, a particular point in our open intervals. Say let f, we assume that this f that we are going to prove that is differentiable and also continuous. Say let this f be differentiable at x naught. This x naught is for a particular point which contain in an open interval a comma b. And we know that for a differentiable function in reanalysis, this is the formula we use. The limit of f of x minus f of x naught all over x minus x naught as x tends to x naught, a particular point in consideration. If this limit exists, then we know that the function is differentiable. And if this function is differentiable, we also know that the function is continuous. Because in reanalysis, every function that is differentiable, it is a continuous function. Take note of that. But if every function is continuous, some of them cannot be differentiable. I can tell you that, example, the magnitude of f of x cannot be differentiable. So, but in this case, we know that in reanalysis that if every differentiable function is a continuous function. So in this case, we assume, because we want to prove that every differentiable function is a continuous function. So for us to be able to prove, we assume that the f, which is the function, be differentiable at x naught, which is a particular point which contain in an open intervals, such that this symbol means such that the limit of f of x minus f of x naught, a particular point, all over x minus x naught. You know that x is in this first bracket. That's why you see this thing down. And we know that x naught in this f of x naught up the denominator, so we bring it down here. So that s of x tends to x naught. If this thing exists, we know that the function is differentiable. So let's prove it if the function is differentiable. Now we come down here. We put f of x here on our left hand side equals to f of x. Then we have f of s on the left hand side. You have f of s on the right hand side. Now, if I put minus f of x naught plus f of x naught, I have not made a mistake, because minus f of x naught plus f of x naught can cancel themselves out. I still have f of x equals to f of x. So if I also multiply x minus x naught divided by x minus x naught, I will still have f of x, because this can cancel this. S of x naught can cancel f of x naught on the denominator, and then minus f of x naught can cancel f of x plus f of x. So I can still left with f of x equals to f of x. So in this case now, I've not made a mistake. So just take note. If you want to start to prove this, just put f of s on the left hand side, equate it with f of s on the right hand side. After doing that, you assume minus f of x plus f of x is the same thing as f, because if you cancel this thing as minus f of x plus f of x is going to give us 0 now. Because if you say minus 1 plus 1, it's going to give you 0. So in this case, I just assume minus f of x plus f of x multiplied by x minus x naught all over x minus x naught. X minus x naught can go into the step 1, and this themselves can cancel themselves out, and this can cancel themselves out. It's still left with f of x equals to f of x. So now we are not making a mistake in this area, but we want to manipulate it. That's why I assume all these things. Now let's look at how to continue to solve this question. Okay, now what we are going to do now is to take limit of both sides. You know that from what we had before was f of x, right, equals to bracket x minus x naught multiplied by f of x minus f of x naught all over x minus x naught plus f of x naught, right? And now we say that you should take limit of both sides. For us to be able to take limit of both sides, we take limit from the left hand side and also on the right hand side. Our left hand side we have f of x, right? So we take the limit of f of x as x tend to what? X naught, which is a specific point in our open interval, our particular point in the open interval. So we take the limit of f of x here, become limit of f of x as x tend to x naught, right? Equals to the limit of, on our right hand side, what we have here was x minus x naught, right? So we have limit of x minus x naught as x tend to x naught. Then you know that all these things together, right? Then plus, you take the limit of this one plus the limit of f of x naught as x tend to x naught. Because this is plus here, that's why I take the limit. It separates this function from this one, this particular one here. That's why I also take the limit of it. Now after doing that, we come down, we still have on our left hand side the limit of f of x as x tend to x naught equals to, if you take the limit of s of the limit of this, you know that what we are saying that if anywhere we see x, we should put x naught. And in this function now there is x here, so we put x naught. Then you have x naught minus x naught at this point here. Then at this point now, if you put x naught in this function where we see x, you know that in this function now, the x that we have is, we don't have a particular x as we have this x. So we take the derivative of this function. But there is no particular x to put in this function. What we have here now is a function of f of x minus x of x naught. It's on the downside that we have x. But for us to be able to get substitute the value of x in this function, we take the derivative. And if we take the derivative of this, we take it by the Reine-Hospital rule. And when we take it by the Reine-Hospital rule, what we have is s prime of f, x. That's why I have s prime of x here. Plus, here, we have limit of f of x naught. So there is no particular x here. There is already x naught here. So we do not have x here. What we have here is x naught. So because of that, there is no need of substituting x to be x naught because there is already x naught here. So that you still have plus x naught. Now we are getting this. You still go down. You say the limit of f of x naught on our left hand side here equals to, you know, x naught minus x naught is 0. That is why I have 0 here. 0 multiply our f prime of x plus our f of x. We are not finished, so let's continue to. Then now what we have now is that, you know that 0 times f of x, f prime of x that we have plus f of x naught, we are going to have 0, right? So 0 plus f of x naught, that's why I got this f of x naught. So our limit now become, our limit of f of x as x tend to s of x naught become f of x naught, which is our particular point we are aiming at. So now, since this thing is differentiable, since f of x is continuous, then imply that f of x is continuous at x equals to x naught. Because when we differentiate it, we have a particular point in it. And since we have a particular point when differentiating it, that means the function is differentiable. And because the function is differentiable, it also means that it's continuous. Because every differentiable function is a continuous function. So thank you very much. If you have any question, you can drop it on the comment section. This particular topic now is from pure applied mathematics in Ring Analysis 1. Drop your comment, drop your question that you have on the comment section. And please don't forget to give us like. That will also help us to motivate us to do more. And also help us to subscribe it so other people can also benefit from it. Because the more you subscribe to it, the more the channel can be able to reach out to other people. Thank you very much. I really appreciate the fact that you are here. And for those that have subscribed to it, thank you very much for supporting us. God bless you all. I'm very proud of you. Thank you.